Welcome to Math Shorts, tantalizing mathematical tidbits that will amaze, entertain, and delight. Math Shorts is brought to you by the Ottawa Zone for Mathematics Education. The Ottawa Zone for Mathematics Education is a chapter of the Ontario Association for Mathematics Education. Information about both organizations can be found in the information for this video.
In this episode of Math Shorts, we're going to be looking at the geometric mean. Now, let's remind ourselves of something that we should know. And that's the arithmetic mean that we will denote by AM. And you might know it by its name, average. And how do we get the average of a bunch of numbers? Well, we take all those numbers and add them up, and we divide by however many numbers that we have. So for example, if I had 32, 4, 64, and 8, if I wanted the arithmetic mean, I'd add those numbers up and divide by 4 because there's 4 numbers, which gives us 27. Now, why would we want to do that? Now, it turns out that if I take my numbers, 32, 4, 64, and 8, and I replace them all with the arithmetic mean, so instead of having that, I've got 27, 27, 27, 27. The sum of these numbers is unchanged. So 32 and 4 and 64 and 8 is 108, which is the same as 27 plus 27 plus 27 plus 27. So this arithmetic mean is sort of a way to kind of smooth things out. It's a way to have one number that if we used it repeatedly, it would give us the same thing as sort of these numbers that are all over the place. So imagine you had a job where you're loading these boxes or loading something every day, and on one day you did 32 boxes, the next day you did 4, the next day you did 64, and the next day you did 8. Well, if somebody just did 27 every single day, then at the end of 4 days, you both would have the same result. So this gives us sort of a nice number that says if things were done consistently, the results would be the same. Now, we know in mathematics, we're not always adding things. So what would happen if instead of dealing with a situation where addition was needed, we ran into a situation where we needed multiplication? Okay, those of you that know a little bit about sequences and series know that an arithmetic sequence is a sequence where each term of the sequence we get by adding the same number every time. Now we also have geometric sequences where we get each term of the sequence by multiplying the previous term by the same amount each time. So just like we've got an arithmetic mean that's related to what we get when we add the terms together, we're interested in a geometric mean, which is going to be related when we multiply things. So we saw our arithmetic mean. If I replaced all the terms with the arithmetic mean, the sum was the same. So since we're dealing with multiplication, if we replace everything with the geometric mean, which we're not sure what that is right now, the product is going to be unchanged. So what that means is for our set, 32, 4, 64, and 8, if I multiply them all together to get 65,536, my geometric mean should be the number that if I multiply it by itself 4 times, I get the same amount, which we know that that means that this number is going to be the 4th root of 65,536, or 16. And that's going to be the same process in general. So, for example, the geometric mean. We're going to use GM for geometric mean. If I've got a whole bunch of numbers, I'm going to multiply them all together, and then I'm going to take the nth root of it, or the root of how many things there are. There's 2 things, I'm going to take the square root. If there's 10 things, I'll take the 10th root. If there's 107 things, I'll take the 107th root of the things. And that's going to be our geometric mean. Okay, so what? We have defined what a geometric mean is. Why would we ever want to use it? We've used our arithmetic mean, or our average, as well as our median and mode, and they've served us well over the years. So why would we ever want to consider something else? Well, let's look at a case. Suppose we had a town that had a population of 10,000. And its population grew by 21% one year, and then the following year it grew by 69%. And we were asked something like, what's the average rate of growth? And again, if we think about what these averages are, is I want one number that if we grew by that percentage each year, it would give us the same result as growing by 21 and then 69. So, probably the first thing that jumps into your head, we see that average. So we jump to our arithmetic mean and we say, well, 21 plus 69 divided by 2 is 45%. So the average rate of growth should be 45%. And a lot of people would be happy with that. But what if we actually look at what happens if we grow by 45% over 2 years, and if we grew by 21 and 69? So let's take a look. So this is what's actually happening. In year 1, first of all, we grew by 21%. Our population was 10,000. So 21% of 10,000 is 2,100. So after the first year, our population would go up to 12,100. The second year, we grew by 69% of this new population of 12,100, which is 8,349. So our new population would be 20,449. Now let's look what happens if we use our arithmetic mean. So we saw that if we just average the 2 percentages, we get 45%. And in terms of what an average does, that means that we should be able to do 45% the first year, 45% the second year, and get exactly the same results. So let's see what happens. So 45% of 10,000, 4,500. So our population would be 14,500. Second year, 45% of 14,500 is 6,525, which gives us a total of 21,055, which is actually bigger than what the real result is. So something's going on here. If we use averages in sort of normal situations, you would get the exact same result. So let's take a closer look at what's happening here. If we do an increase of 21%, that really means that we're starting with our whole thing, which is 100%, and we're adding 21% more, which means that we're doing 121% of the previous value. Similarly, an increase of 69% means that we're 169% of the previous value, which means that we can actually do our computation in a much more compact way than we did before. We don't have to calculate the increase, added on, calculate the increase, added on. If we start with our 10,000, an increase of 21% means we're going to be 121% of what we were before. So if I multiply by 1.21, that actually gives me the end answer for year 1. And then for year 2, going up by 69% means I'm multiplying by 1.69. I can do this all in one big computation. 10,000 times 1.21 times 1.69 gives us 20,449, which agrees with our actual population. Now, if we look at what's happening, we actually got our result by multiplication. We're multiplying these two factors together. So our problem involves multiplication. So that sort of suggests the geometric mean. So let's look at the geometric mean of these two numbers. So the geometric mean would be multiply them together, take the root, there's only two of them, so it's going to be the square root, which turns out to be 1.43, which, if we think about what that means, we're going to be 1.43 or 143% of the previous year, which means that we had an average growth rate of 43% as opposed to 45%. Now, let's check this one out. So if we go back to our computations that we did before, on the left, there's our actual. We know that we had 20,499. So now let's use 43% instead of 45%. So if I use the geometric mean, the first year, the 43% brings us up to 14,300. And in the second year, look at that. It exactly matches, although I can't. I have a typo here. So this should be a 4. Oh well. But they are exactly the same. So we saw that the geometric mean could be used in different situations where we've got multiplication. And we saw in that percentage example that it gave us an answer that was slightly less than what we got when we did the arithmetic mean, or the one that we're used to calling the average. Now, if we go back to our first example, the 32, 4, 64, and 8, remember, if we calculate its average by adding them up, or its arithmetic mean by adding them up and dividing by 4, I get 27. And the geometric mean, by multiplying them all together and taking the fourth root, I get 16. And look at this. In this case, the arithmetic mean was bigger than the geometric mean as well. So you might start to wonder, is the arithmetic mean always bigger than the geometric mean? Well, let's look at a really simple case. So we'll look at the case of just two numbers. Let A and B positive numbers. Now, with the geometric mean, because we're taking roots, and some roots aren't defined for negative numbers, we're only going to look at the geometric mean when all of our numbers are positive. So, let's suppose we have two positive numbers. Then, if I take the square root of each of them, because they're positive, I can do that, and then subtract them, and then square the result. Well, let's look at what happens. Well, if these two numbers are exactly the same, when I square root them, their results will be the same. When I subtract them, I'll get 0. If A is bigger than B, then its square root's going to be bigger than this, and then this will be positive. If A is smaller, then this will be negative. Now, when I square something, I multiply it by itself. And we know a positive times a positive is a positive, and a negative times a negative is a positive. Which means that no matter what, when I do this, I'm never going to get a negative number. That result is always going to be bigger than or equal to 0. And the only time it's going to be equal to 0 is if A and B are exactly the same number. Now, if this is bigger than 0, if I divide it by 2, that's going to be bigger than 0 as well. Okay, so what? Well, let's do a little bit of algebra on this thing and see what it gives us. So if I take that and expand out this product on the top, I know that a minus b squared is a squared minus 2 times root a root b plus root b squared. And then if I simplify, root of a squared is just a, root of b squared is just b, and root a times root b is just root of ab. And for the root part, I've got 2 of them, and I'm dividing by 2, so the 2's actually cancel for this part, but not for this part. So this simplifies to, I get my a and b are still divided by 2, and I get minus this root ab. Okay? Now let's put this together with this, and what do I get? I get a plus b over 2 minus root ab is always going to be greater than or equal to 0, which means that a plus b over 2 is going to be greater than or equal to root ab, but look at this. Add two numbers, divide by 2. Multiply two numbers, take the square root. Those are just our arithmetic and geometric means. So for two numbers that are positive, the arithmetic mean is always going to be bigger than or equal to the geometric mean. And the only time they'd be equal is if the two numbers were exactly the same. And it turns out that this holds in general, and we call this the arithmetic geometric mean inequality, or the AMGM inequality. And it says that if I've got any set of positive numbers, the arithmetic mean, which is add them all up and divide by how many there are, is always going to be bigger than or equal to the geometric mean, what we get when we multiply them all together and take the root. Okay, so that was a nice algebraic proof of the AMGM inequality. So since we're dealing with the geometric mean, let's look at a nice geometric demonstration of this inequality. So in this case, we're dealing with two positive numbers, and I'm going to use line segments of the length of our given numbers to represent our two numbers. So our two numbers a and b are going to be line segments of length a and b. I'm going to put them together to make one big line segment whose length is a plus b. And I'm going to create a semicircle where this line segment of length a plus b is the diameter. So since a plus b is the diameter, if I draw in the radius is going to be half the diameter, which is going to be a plus b over 2, which is the arithmetic mean. Now, I'm going to claim that if I draw another line segment perpendicular to our diameter, right at the point where the a and b come together, I'm going to claim that the length of that is the geometric mean. Now, if that's true, then it's obvious that the arithmetic mean is going to be bigger than or equal to the geometric mean, because the longest this line segment could be would be the radius, and that would only be in the case when a and b are the same thing and this geometric mean lies right on top of that arithmetic mean there. So that's the whole crux of what we're trying to show, but I'm going to try to demonstrate my claim. So for now, I'm just going to call that length x, and I'll see if I can show that that's equal to what the geometric mean should be. So to get on with that, first thing I'm going to do is I'm going to draw a triangle using the endpoints of our diameter here and the point where that line segment joins as the third point. Now there's a property in geometry that says that if you have a semicircle and use the diameter as the side of a triangle and you put the third vertex of the triangle anywhere on the semicircle, it turns out what you'll have is a right angle triangle. The diameter will be the hypotenuse, and this point here will give us a right angle. So if I look at my right angle triangle, I've got two acute angles. I've got one down here, the small one that I'm going to mark in brown, and this bigger one that I'm going to mark in yellow, and that will be useful later on. Now let's put back in this line segment x, and remember that that was perpendicular to a and b. So I get this right angle over here, which means that I've got a little right angle triangle on the left. Now if I look, one of the angles is brown, one of the angles is 90 degrees, and I saw from my big triangle that brown plus 90 plus yellow are the three angles of a triangle. They add up to 180. So brown plus 90, the angle that I'm going to have up here is going to have to be yellow. Which means that this triangle in red is actually similar or a slightly smaller copy of that big triangle. Kind of neat, but who cares? Well, let's keep going and look. If we look at the other side, again, this is going to be 90 degrees over here. I've got yellow and 90, and we know that yellow and 90 and brown add up to 180, which means that this angle up here has to be brown, which means that this blue triangle is similar to the big triangle, which also means that the red and the blue are similar to each other. Now, the nice thing is this side that I'm after, x, is in both of these triangles. And that's the thing that I'm after. So we know with similar triangles, the ratios of corresponding sides is constant, which means that if I look at the side that's across from the brown in the red triangle and the one that's across from brown in the blue triangle, and if I divide that, I'm going to get exactly the same if I look at the pairs that are across from yellow or the pairs that are across from the 90 degrees. So let's do that. I'm after x. So x is across from brown in the red triangle, and it's going to go with the one that's across from brown in the blue triangle, which is b. So x over b. And that should be the same as the other pairs of sides. Now again, since I'm interested in x, I'm going to look at the blue triangle. I'm going to say, oh, x goes with yellow. And in the red triangle, yellow goes with a. Now I set up this ratio so it's red triangle over blue triangle, so I have to do my ratios the same way. So if I go to my yellow angle, it's going to be a over x. And those two things have to be the same. Okay, let's do a little algebra. I've got these fractions. Let's multiply both sides by x and b to clear those fractions. And I get x squared is going to be ab. But if I take the square root, that means x is going to be the square root of ab. And that's just our geometric mean. So we've shown that this thing is indeed the geometric mean. And we get a nice visual confirmation of our AM-GM inequality. I hope you've enjoyed this episode of Math Shorts. Tune in next month for a new episode. Until then, keep exploring your mathematics.